Covers Griffiths E&M section 5.4.1, the magnetic vector potential. All right, so the goal in the second part of this course has been to calculate the magnetic field. We have a couple different tools in which we can do that. We can go ahead and calculate it from the Biot-Savart law, basically taking the current distributions, integrating them, kind of like Coulomb's law. Or if we have a symmetry, we can use an Amperian loop to exploit that symmetry. Right. We kind of had the same strategy before for electrostatics. We had Coulomb's law, we had Gauss's law, but we also had another thing we could do, which was defining the electric potential. All right. So in electrostatics, we had a curl-less electric field, which allowed us to define a scalar potential. And then if we took the gradient, negative gradient of that potential, we got E. So we found a scalar V, took a gradient, boom, done. Okay. We can't do the same thing for the magnetic field because the magnetic field is not curl-less. All right. So instead of doing that, we are going to go ahead and define or introduce a particular type of potential. We're going to define a vector potential. Okay, there's a difference between electrostatics and magnetostatics here. We'll call that that vector potential A. And we want to go ahead and build this vector potential such that the magnetic field is now the curl of that vector potential. All right, just like we took the gradient of something before to get the electric field, now we're going to take the curl of that electric field, or that vector potential to get the magnetic field. Okay. We're going to go ahead and say that the vector potential has a particular quality. And we're going to say that it is divergence-less, meaning that the divergence of our vector potential is 0. Okay. I'm just going to go ahead and say that as a definition. If you want more, Griffiths goes through a more complicated argument about why that can be the case on page 243. All right. But I'm okay with taking that at face value. Okay. We're going to define some field that has no divergence. And if I take the curl of that field, I get the magnetic field. All right, so let's go ahead and use Ampere's law in differential form. All right, del cross B, curl of B is just the curl of A. We can rewrite that via something from chapter 1 as the gradient of the dot product, or the divergence of A minus del squared A. Right. This is equal to, because we started here with Ampere's law, it's mu naught J. But I defined this to be 0. So that term is 0. Okay. So now I have this expression that grad squared A is equal to minus mu naught J. All right, remember we had something similar to this in chapter 2. Remember we had Poisson's equation. Right? Del squared V is equal to minus, our charge density over epsilon naught. This was Poisson's equation. This is also Poisson's equation, except now there's 3 of them. That's a vector, so you have 3 different components in 3-dimensional space. Okay. So this is Poisson's equation. In 3 dimensions. All right, we like to simplify Poisson's equation by looking at regions of space where, for electrostatics, where there are no charges. So we do this for regions of space where there are no currents. Right? Specifically in the region where there are no currents, that means that we have Laplace's equation. Like we did in the electric potential case, we stated that the charge, if charges were not at infinity, we could set our reference at infinity and find the difference between the difference in the electric potential from any point in space with a reference point at infinity. Okay. We're going to go ahead and do the same thing here. We're going to go ahead and say that if the current density goes to 0 at infinity, we can find the magnetic vector potential through the integral of the current density with r hat d tau prime. Okay. So integrate all the current, you can get the magnetic vector potential. It looks a lot like the expression for the electric potential, except this is a vector, so you have 3 integrals to do, but it's still probably easier than calculating the magnetic field using the Biot-Savart law.